Okay, we are recording. So we will start. The committee has already done its discussion over email so that we could start on time. So I am happy to introduce Ryan for his dissertation defense. Do you need me to move? No. Okay. Happy to introduce Ryan for his dissertation defense. Ryan has been, yeah, Ryan is waving. Ryan finished his bachelor's in the University of Alberta in 2014 and then came to OU. And he came to OU already knowing that he wanted to do machine learning for weather. And it's been a lot of fun. In fact, I'm really sad that he's graduating. He finished his master's in 2016 and has now been working at the nexus. He wrote this bio, but I agree with it. He's been working at the nexus of machine learning and meteorology for 8 years. He was doing machine learning for meteorology before he came to OU. So I'm looking forward to this presentation. And the rules, as we usually run them for dissertations, are that the committee can interrupt at any point. I ask that the audience interrupt if they have confusion questions, but if they have a question that's just sort of can wait to the end, I would prefer that the audience will wait on that, especially because your audience is up to 75 people now. So go ahead, everybody can see your screen. And I guess the other way to handle it is if the audience has a question that, you know, you need to do something, but you don't want to interrupt, you could put it into the chat as well, and I'll keep an eye on the chat.
All right, am I good now?
You're good, and I'm gonna mute myself so that it's just you. And I'm also gonna turn off my video so there's no issues.
Okay. Well, good morning, everyone. Thank you all for coming. Good afternoon if you're in Newfoundland or Europe. So this is my dissertation defense for the OU School of Meteorology. The title is called Using Deep Learning to Improve Prediction and Understanding of High Impact Weather. My contact information, in case you don't have it, is up there at the top of this first slide. If you want me to send the slides afterwards, if there's anything you want to dig into, and also there's some hidden slides at the end, just let me know. The references are all at the end as well, so where you see a citation. If you want to get the full paper, all that stuff is in the slides. My committee for my dissertation is Amy McGovern, who's my chair, who just introduced me, and also Jason Furtado, Jeff Becerra, Michael Richmond, Andrew Fagg, and Justin Metcalf. Oops. All right, so I'm going to start with a brief outline, just summarizing the contributions that I've made to the field throughout my PhD and in my dissertation, and then I'll jump into it. So I've developed and tested deep learning models, specifically convolutional nets, for 2 tasks, which are tornado prediction and front detection. My main contributions to tornado prediction: I've developed a model that's competitive with the current operational machine learning model, and it's promising for future use. And we have a proposal underway to put it into operational use, so I'll talk about that. I've also used novel interpretation methods for the deep learning models to understand the physical relationships that they've learned. And then as for my contributions to front detection, I have a model that automates detection of warm and cold fronts over a large area. It's North America plus the surrounding oceans. I've created and analyzed a 40-year climatology of those warm and cold fronts, and I've compared that climatology with the few previous climatologies that exist that investigate the influences of ENSO and long-term change on warm and cold front activity. So overall, I've demonstrated that deep learning can improve both the prediction and understanding of 2 very different high-impact weather phenomena. So part 1 of this presentation is going to be on tornado prediction, and part 2 of this presentation is going to be on front detection. So to motivate the tornado prediction stuff, the skill of National Weather Service, or NWS, tornado warnings, they're the people responsible for issuing warnings all throughout the country. That skill has stagnated in the last decade or so after steadily improving since the 1950s. And in that time that warning skill has stagnated, the amount of data and tools available to forecasters has exploded. So you'd think these forecasts would be getting better. They now have dual polarization radar, high resolution satellite with GOES 16 and 17, convection allowing models down to 1 and 3 kilometers that are run operationally, et cetera, et cetera. One of the main problems with having this massive amount of data and tools is that they don't explicitly resolve tornadoes because they just don't have the spatial resolution to do so. Tornadoes are hundreds of meters across, and the best resolution of these data sets and tools is usually several kilometers. So that leaves the forecasters to mentally post-process a whole bunch of big data into tornado predictions and warnings, and that can lead to cognitive overload. But that post-processing can also be automated by statistical methods like deep learning, which excels with big data. So specifically, the type of deep learning model I use is convolutional neural nets, or CNN. I'm just going to say CNN from now on. It's a deep learning method that's specially designed to learn from gridded data. So in traditional machine learning, for a typical neural net instead of a convolutional neural net, for example, or a decision tree or logistic regression or something like that, if you have gridded data, you can't just feed that gridded data straight into your model to train it. You have to convert all that gridded data to scalar statistics as a pre-processing step. And that destroys spatial information that could otherwise be exploited by the machine learning model. The nice thing about CNNs is they can see the entire grid, so they can exploit spatial structure everywhere in that grid, and that generally improves skill. So in this little picture at the right, you're seeing, this isn't my work, this is from someone else. I wanted to start off with a cute pet picture. So someone has trained a CNN that detects, it looks at photographs and tells whether there's a cat or a dog or something else in the photograph. And the red pixels are the ones that contain dog evidence, and the green pixels are the ones that contain cat evidence, according to the CNN. So you can see that the CNN can zoom in on the parts of the grid that are relevant for making different classifications. So specifically for tornado prediction, what I've done is I've used a CNN to forecast the probability that a given storm will be tornadic at some point within the next hour. So it's a 0 to 1 hour lead time frame. So next I'm going to talk about the input data, and then I'll go back to CNNs and talk some more about their inner workings before I show you results. So I use 4 different data sets to do tornado prediction. I use radar images from MERS and GridRAD, both of which are multi-radar data sets, and I'll describe those in the next few slides. I use proximity soundings from the RAP, or the Rapid Refresh Weather Model, and then I use tornado reports. So the tornado reports are used to create labels. I label each storm a yes if it produces a tornado in the next hour, a no if it doesn't, and then the proximity soundings and radar images are used as predictors to determine which storms are going to produce tornadoes. So as promised, I'm going to talk about MERS and GridRAD on the next few slides. MERS and GridRAD are multi-radar data sets. They're created by merging data from all the WSR-88D radars in the continental United States. You can see a map of all those radars on the right-hand side. There's about 140 of them. Both of these data sets, MERS and GridRAD, have 5-minute time steps, and the data sets overlap for 1 year. So the MERS data set runs from 2005 to 2011, and GridRAD runs from 2011 to 2018. Since there's only 1 year of overlap there, I've decided to use that as the testing year. So the MERS model is trained and validated on different periods. The GridRAD model is trained and validated on different periods. And then that 1 year is set aside for testing at the very end. So this is what the radar data look like. This image you're seeing here is for GridRAD. GridRAD has approximately 2-kilometer horizontal spacing, and it contains 3D fields of 4 different variables. I'm only showing you 3 different heights here. So at the top, you're seeing 2 kilometers above ground level, or AGL, and then you're seeing 6 and 10 kilometers above ground. This data set has data from 0 to about 20 kilometers above ground level. And in the left-hand column, you're seeing reflectivity. Then as you go towards the right, you're seeing spectrum width, and then vorticity, and then divergence. This next picture here is showing you what the MERS data set looks like. Oh, and also I should note that this radar image I'm showing you is storm-centered with storm motion pointing towards the right. And every radar image you're going to see throughout this talk is going to be formatted the same way. It's a storm-centered radar image. The horizontal extent is 48 by 48 kilometers, and the storm is moving towards your right. So MERS contains 2 different radar variables. One is reflectivity with approximately a 1-kilometer horizontal spacing. In this picture here, I'm showing you reflectivity at 12 different heights for the same storm. And the other variable in MERS is azimuthal shear, which has half the grid spacing or twice the resolution of reflectivity. So it's at 0.5 kilometer resolution. Azimuthal shear is just defined as half of vorticity, or half of the rotational wind component. Instead of being defined on a 3D grid, azimuthal shear is maximized over 2 layers in the data set. So we have low level shear and mid level shear. Low level is a maximum from 0 to 2 kilometers above ground, and mid level is a maximum from 3 to 6 kilometers above ground. And those variables were defined that way to detect low and mid-level mesocyclones, respectively. So now I'm going to talk for a couple slides about how I process the input data. I'm not going to go too far into the weeds on this stuff. Each input to the CNN is 1 storm object. And when I say 1 storm object, I mean 1 thunderstorm cell at 1 time step. So when you look at this GIF on the right-hand side, if you just freeze frame that GIF at 1 time step, all the black outlines are showing you 1 storm object each. And then the multicolored lines are showing you the tracks of these storms as they progress over time. And that's an output from a tracking algorithm I've developed with Cameron Homeyer, who's the creator of the GridRAD data. So the first pre-processing step is just outlining the storm cells or the storm objects at each time step. The second step is tracking the storm cells over time. That's done separately for the MERS and GridRAD data sets. So on that last slide, you were seeing a GIF of storm tracks in GridRAD. Now you're seeing a GIF of storm tracks in MERS. Qualitatively, the tracks and the storm objects are similar, but the 2 data sets are somewhat different. The third pre-processing step is creating storm-centered radar images to be used as predictors to go into the CNN and do machine learning. So there's one storm-centered radar image for each storm object. So these radar images I was showing you on the last few slides, each one of these is a storm-centered image, and it's around one storm object. So it's representing one thunderstorm cell at one time step. And as I said earlier, these are on an equidistant grid. It's 48 by 48 kilometers, and storm motion is always pointing towards the right. Then the fourth pre-processing step is creating proximity soundings. These are soundings representing the near storm environment that the storm will be evolving in over the next hour. And again, there's one of these per storm object, and the proximity soundings are used as predictors along with the radar images. So the importance of this is that the radar image is a representation of the current storm. It shows you what the storm looks like right now. And then the proximity sounding tells you what the environment around the storm is going to be in the next hour, which partly determines how it's going to evolve. The fifth pre-processing step is linking tornado reports to storms, because I need to know which storms are responsible for a tornado and when they're responsible for a tornado, so I can create my labels, which is the sixth and final pre-processing step. So there's one label for each storm object. When I say label, these are the correct answers that machine learning or the CNN is trying to emulate. So these are the answers it's being evaluated against. So a storm is labeled yes if it's tornadic in the next hour, at any time in the next hour, otherwise it's labeled no. And that's what machine learning is trying to get right. So as promised, I'm going to talk a little bit about the inner workings of CNNs. I'm not going to go into nitty-gritty details. I'm not going to show you the mathematical equations because we'd be here all day. But I want to just give you a high-level understanding of how CNNs work. So CNNs have three main components, which are the convolutional layers, pooling layers, and dense layers. So on this slide, I'm talking about the convolutional layers. Each convolutional layer is made up of convolutional filters that detect spatial features. So that little yellow window that's moving over the larger green image is a convolutional filter, and the weights in the filter are the little red numbers in the bottom right-hand corner. Convolutional filters are not something super new or super fancy. They've been used in image processing for decades to do things like blurring, sharpening, edge detection, etc. So if you've used Photoshop and you've done any of those operations, they've probably used a convolutional filter. The difference is that in those traditional applications, the filter weights are fixed. They're usually small integers like the ones and zeros you see in the filter in this animation. But in a CNN, you initialize those weights all to random values, and then they're learned over time in a way that optimizes your prediction or decreases your loss function. The second main component of CNNs is pooling layers. These downsample the grid or the image to a lower resolution, so they increase the grid spacing. Usually you keep on doubling the grid spacing as you go along. The benefit of that is the shallower convolution layers that come earlier in the CNN. They can learn features that are on the original grid scales. They can learn fine scale features. And then as you keep doubling the spacing of this grid, the convolution layers that come later and later are learning successively larger and larger scale features. And often in meteorology, features at multiple scales are important for prediction. You know, features on the microscale, mesoscale, synoptic scale, etc. Finally, the third component of CNNs are dense. Dense layers are fully connected layers. Sometimes people call them in the literature. Sometimes they also call them hidden layers. They're the same layers that you see in a traditional neural net that doesn't do any convolution. So they're completely spatially agnostic. And the job of dense layers is that they transform features created by the convolutional and pooling layers into a final prediction. And in this case, the final prediction is the probability of a tornado happening in the next hour. So to summarize all the stuff I just told you, and you're going to see a little flow chart on the next slide for my particular problem, the convolutional and pooling layers transform gridded data into features. The dense layers transform those features into predictions. And that whole process is automated, going from spatial grids to a final prediction of whether or not there's going to be a tornado. And the CNN learns both of those transformations simultaneously. So on this next slide, I'm showing you the CNN architecture for GridRAD data. Like I said earlier, I have two radar data sets. I have GridRAD and mirrors, and I've trained a separate CNN with each data set. I'm not showing you the architecture for mirrors just because I didn't want to show two huge complicated figures like this. So what you're seeing in panel A is what I showed you earlier, the storm-centered radar image, only showing you 3 of the 12 heights. I use heights from 1 to 12 kilometers above ground level. And there's also a proximity sounding that goes into the CNN, and it does convolution and pulling over the proximity sounding. I'm not showing that, again, just for the sake of simplicity. And then if you look at panels B to E, they're showing you just with a diverging color scheme, red values positive, blue values negative, the feature maps that are created by the convolution and pooling layers. So in this case, I have the input, which you can see with the little flowcharty bubbles at the top and on the right-hand side. I have the input radar image, and it goes through convolution pooling, convolution pooling, convolution pooling. Then all the layers discovered by the convolution and pulling layers are flattened into just a single 1D vector. And then there's a whole other part of the CNN that does the same thing with soundings, that does convolution and pulling over soundings. Those sounding features are concatenated to the vector of radar features. And then all these features, there's almost 3,000 of them, 2,816. They're fed through two dense layers at the end to just transform those 2,816 values into one final prediction. I'm going to take a drink of water before I keep talking. All right, so I'm going to talk a little bit about the hyperparameter experiment that I did to create the final CNN for tornado prediction. Again, I don't want to get too far into the weeds. The main point of showing these next few slides is to emphasize that when you're doing machine learning for whatever your particular task is, it's usually not sufficient to just download someone else's machine learning model out of the box and apply it to your problem. There's lots of these characteristics you have to tweak. So a hyperparameter is a characteristic of the model itself, such as number of layers, the number of neurons, etc. And that's something you have to choose a priori, and it's something that can't be modified during the training process. So the training process tweaks the weights in those convolutional filters and in those dense layers and whatnot. But the training process can't change, for example, the number of layers in the net. That's just fixed. It's something you have to decide a priori and then go with it. So the model weights are fit to the training data, and then the hyperparameters are fit to the validation data, which is why I've split my data into 3 partitions, being training, validation, and testing. So to create the final tornado model, I performed a grid search over 4 different hyperparameters. The main purpose of these hyperparameters is they all control overfitting, because I found that to be a big problem for weather data in general, where the model does really well in the training data, but then doesn't generalize outside of the training data. So the 4 hyperparameters are the weight for L2 regularization. That's a way to make sure the weights inside the model don't get too big. The rate for dropout regularization, that's a way to make sure the weights inside the dense layers don't all co-adapt to the same storm at the same time and sort of overfit the same storm. Then the number of dense layers at the end of the model, and also something called data augmentation, which I turned on or off. And I'll talk to you about data augmentation in the next couple slides, because I think that was one of the more novel things that I've done. And to choose the best model, I chose the model with the highest AUC, or area under ROC curve, on the validation data. So that was how I decided on what the best hyperparameters were. So here I'm showing you the results of the hyperparameter experiment for the CNN trained with GridRAD data and the CNN trained with MIRS data. The value being shown in the color scheme is AUC, or area under the ROC curve, on the validation data. There's a lot to digest here. The main things I want to point out are that, especially for GridRAD, less so for MIRS, but the general trends here are that the models did better when they were trained with 2 dense layers instead of 1, and when data augmentation, or DA as I've abbreviated it here, is turned on instead of being turned off. So data augmentation helped. So now I'll talk to you about what data augmentation is. It's a procedure you use during training, and never again, you don't use it during validation or testing to evaluate your model. It's just during training. It's something that allows the CNN to generalize better or overfit less. So specifically what you do is you apply small perturbations to the predictors. You make tiny tweaks to these radar images, and you assume that the label, which is whether the storm is tornadic or not in the next hour, stays the same. So you assume that these little tweaks to the radar images don't affect the tornado potential of the storm. So specifically, there's details at the bottom about the exact 17 perturbations I applied to each storm-centered radar image. I'm not going to go into the details of that. I'll just say that I did 4 horizontal rotations, 8 horizontal translations, and I added Gaussian noise 5 separate times to each of these images. So here's a little mock-up of what that looks like. I'm showing you what data augmentation does for reflectivity at 3 kilometers above ground, but I applied the same perturbations in tandem to all radar variables at all heights. So the original image in panel A here, that's what the radar data actually looks like. And then panel B is showing you what happens after translating 3 grid cells to the bottom and 3 grid cells to the right. Then panel C is showing you what happens after rotating 30 degrees, and panel D is showing you what happens after adding some Gaussian noise. So now I'll jump into model evaluation. We want to know how well the models did. So I'm going to show you a couple ROC curves, a couple performance diagrams, and then I'm going to show you what I call extreme cases. So the cases where the model did really well and the cases where the model didn't do so well. So on the right-hand side here, I'm just showing you results on all the testing data. The testing set which comes from the year 2011. It contains the same storms for both the MERS and GridRAD data. I just, at every time step, I matched the MERS and GridRAD storms to make sure that for the MERS and GridRAD models, I'm testing on the same storms, except they just have different radar representations in the two data sets. So at the end, I ended up with 117,000-ish storm objects. 3.19% of those are tornadic in the next hour. So on panel A at the top there, you're seeing the rock curve. The AUC, area under curve, for both models is about 0.94. The 0.9 is generally considered the threshold for excellent performance. And rock curves, the nice thing about them is they're not sensitive to event frequency. So even for a rare event that only happens 3.2% of the time, you can get a really nice looking rock curve. The same isn't true for the performance diagram, because when you have a rare event, it's really hard to get to be in the top right portion of that diagram where you want to be. It's really hard to get a high probability of detection with a low false alarm rate. It means you have to issue a lot of positive forecasts, and you have to be right on the vast majority of positive forecasts you issue. And we just know that's not the case for tornadoes. The vast majority of tornado warnings are false alarms, and that's for human tornado warnings, and that's true for the machine learning model as well. So jumping to the next slide here, I alluded at the beginning that there's a machine learning model currently used in operations to forecast severe weather on a short time scale, on a storm by storm basis. It's called Prob Severe. So I looked at the evaluation results for Prob Severe from their paper in 2018, and where Prob Severe fits on this performance diagram is the black star down here. So it achieves a lower CSI with a higher event frequency. Their event frequency is about 5%. However, I'll note that the comparison isn't apples to apples. I'm not trying to make a claim that I'm doing better than Prob Severe. They use a real-time version of the MERS data, which has undergone less quality control. They also predict the probability of all severe weather. So it's a tornado or large hail or damaging straight line wind. They don't separate it by phenomenon, at least in this 2018 paper. Nonetheless, I think this comparison suggests that the CNNs I developed would be useful in an operational setting. The last slide you're going to see with rock curves and performance diagrams is this one. This is the same as the last two slides, but now I've gotten rid of weak tornadoes, so the EF0s and EF1s are gone from the testing set. Because weak tornadoes, we know there's a problem in the database where they're often not reported, especially in rural areas and at night. So this leaves us with about 114,000 storm objects, and 1.33% of those are tornadic in the next hour. So we've decreased our event frequency here. If the model skill were independent of tornado strength, by decreasing event frequency, you'd expect to see the same AUC because that's not sensitive to event frequency, but you'd expect a big decrease in CSI because that is sensitive to event frequency. However, if you go back and forth between these two slides, you can see that AUC increases and CSI stays roughly the same, which suggests that the models do better for strong tornadoes, which is not a big surprise because strong tornadoes are better labeled in the reports database, and also they tend to have clearer radar signatures. All right, so the next few slides are going to wrap up model evaluation for tornado prediction. As I said earlier, I'm going to show you extreme cases. So I'm showing you the 100 best hits, worst false alarms, worst misses, and best correct nulls. So the way I define those, for example, the 100 best hits are the storms labeled yes, they do produce a tornado in the next hour, and the CNN got them really well. It got them with high probability. And another example is the 100 worst misses are storms that are labeled yes, they produced a tornado in the next hour, but the CNN forecast a really low probability, so it missed those events. And I'm going to show you a bunch of composites on the next few slides. The composites for each set are created by a method called probability match means. Instead of just taking the mean grid point by grid point, PMM preserves spatial structure better than taking the mean grid point by grid point, which is why I did that. So here you're looking at the composite for the 100 best hits. I'm showing you for the GridRAD model only. These composites are really similar for the MERS model, so in the interest of time, I'm just showing you one. So for these 100 storms, they all produce tornadoes in the next hour, and the average forecast probability was over 99%. So the CNN really did a good job with them. And one thing you'll note is that in general, this composite looks like a supercell. And I have arrows pointing to the relevant features that would suggest this is a supercell. So we see a hook echo in the low-level reflectivity field at 2 kilometers above ground. We see strong low-level convergence, which is just the negative of divergence. We see strong upper-level divergence. We also see a deep reflectivity core. So all those things indicate a strong deep updraft. And we also see a deep mesocyclone with strong rotation. Now we'll flip forward to the 100 worst false alarms. And one thing you'll notice, I'll go back and forth between these two slides a few times so you can see the differences. And there's really not many. other than as you go from the best hits to the worst false alarms, that hook echo in the 2-kilometer reflectivity field disappears. It's in some of the worst false alarms, but not in others, and it ends up not showing up in the composite. But really, the worst false alarms and best hits look very similar. So I looked at the 100 worst false alarms. I investigated them individually, and I found that 76 of the 100 storms also have an NWS tornado warning associated with them. So they're mostly false alarms for the human forecasters as well. I think the most likely reason that there's such a similarity between best hits and worst false alarms is caused by the dichotomous labeling we apply to these storms, where a funnel cloud that almost touches the ground is called a no, and a weak tornado that only briefly touches down and does minimal damage is called a yes. So we're taking this continuous spectrum of phenomena and dichotomizing it. Now I'm showing you the composite of the worst misses, also for the grid-rad model. These are storms that all did produce a tornado, but the average model probability was 9%, so it didn't do a good job. You'll notice, going back to the first two composites and now going to the worst misses, the reflectivity core is much weaker, it's much shallower. There's very little reflectivity left at 10 kilometers above ground. And also the storm has a much more linear or stringy structure. So I inspected these storms individually as well. I found that 67 of the 100 are part of quasi-linear convective systems, or QLCSs. And QLCSs are a common failure mode for humans and other forecasting methods. And that's been known for quite a while now, that they trip up tornado forecasting in general. Finally, I'm showing you the best correct nulls here as a composite again. These are all non-tornadic storms, and the model did a really great job. Its average forecast probability was 0.004% for these storms. And you can see that the storm basically looks like junk. If you're a meteorologist making tornado forecasts, you wouldn't feel menaced by this storm either. And by inspecting the storms individually, I found these are mostly short-lived cells in mesoscale convective systems, often behind the leading line. So the last thing I'm going to talk about for tornado prediction before I jump into front detection is model interpretation. So I've used some recently developed interpretation methods like class activation maps and saliency maps, which you're going to see, to understand the physical relationships that have been learned by the CNNs. I'm only going to show you a few results here in the interest of time. If you'd like to see more detail, some of this stuff is published, in 2 recent papers. So based on the previous literature from numerical modeling and observational studies, tornadoes are a pretty well-studied phenomenon, and people have found a lot of these features that are conducive to tornadoes. So I was expecting / hoping to find these in the CNN interpretation as well. So some of those things are that you want a deep reflectivity core indicating a strong updraft. You want a strongly rotating compact low-level mesocyclone. For supercell tornadogenesis anyways, the low-level mesocyclone generally has to be strong to ensure tornadogenesis. It's not enough to have just a strong mid-level mesocyclone. You'd also expect that discrete storms would favor tornadoes, especially strong tornadoes. Strong low-level wind shear, low-level relative humidity, and low-level instability in the sounding. And also weak reflectivity in the rear flank downdraft. There's been some work in the last couple decades that suggests if you have a lot of reflectivity in the rear flank downdraft, that suggests you have a lot of precipitation loading and evaporative cooling, and that leads to too much negative buoyancy for that air to be re-ingested back into the updraft when it hits the ground. So that causes that really cold, negatively buoyant air to undercut the mesocyclone and preclude tornadogenesis. So the first method I'm going to show you results from is class activation maps. This slide is just telling you, defining what class activation maps are. It's pretty simple. Class activation is the amount of evidence for the positive class, according to the CNN, of course. And the positive class here is tornado evidence within the next hour, or the evidence of there being a tornado within the next hour. So here I'm showing you, these are composites for the grid-rad model, which you've seen before. So the color maps in the background are the same as what you've already seen. You're seeing the best hits and the worst misses. The only difference is on top now, you're seeing class activation in these black line contours. So for the best hits, you can see that tornado evidence is maximized on the right rear flank of the storm, and at the lowest level as well, which is where we'd expect to see a tornado in a supercell. Then for the worst misses, you can see that tornado evidence, the maximum here, if you look at the color scale on the right-hand side, it's logarithmic. So the maximum tornado evidence for the worst misses is about 10 times smaller than the max tornado evidence for the best hits. But you'll see where the evidence is maximized is basically where the highest vorticity and highest reflectivity overlap. And also the area outside that final white contour is an area with 0 tornado evidence, according to the CNN. So the CNN seems to have implicitly learned that storms with linear structure don't produce tornadoes. because the part of this storm that would tell you it has a linear structure is the part that has zero tornado evidence. Here I'm showing you the exact same thing, but this is for the MERS model instead of the GridRAD model. You'll notice there are some differences, but at a high conceptual level, the class activation maps are really similar. These arrows, I haven't changed the text that goes along with these arrows. I've just changed their positions a little bit. So the results for class activation maps and for the other interpretation methods as well are mostly similar between the MERS and GridRAD models. That's a really encouraging sign because often machine learning doesn't give you that much generalizability. Often you change one little thing about the inputs and your results become completely different. And the MERS and GridRAD models differ significantly. They differ in the architecture, of course, the radar data set that they're trained with, and they're also trained on two completely different sets of years. So the second interpretation method is called saliency maps. This slide is telling you what saliency is. The next slides are going to show some results. Some people call saliency sensitivity, pick your terminology. It's just defined by this equation. So it's di p di x linearized around x equals x naught, where p, the numerator, is tornado probability, x, the denominator, is one input value. So it's one predictor at one of the grid points, could be reflectivity at grid point ijk. And saliency is a linear approximation to this derivative around the point x equals x naught, where x is the value in an actual storm. So here I'm showing you composite of saliency maps for the best hits. These are for the GridRAD model again. You've seen this composite a few times now. The color fields in the background are all the same. That's just what the storm looks like. The contours on top are saliency. Solid contours mean saliency is positive, so tornado probability increases with the radar value underneath, and then dashed contours mean the saliency is negative. So three things I want to point out here. Tornado probability increases according to the model, increases with reflectivity inside the core, especially at the upper levels, more so at 10 kilometers than at 6 and 2. Tornado probability increases with spectrum width at all heights. Spectrum width is proportional to mean wind speed and turbulence. And also tornado probability increases with vorticity inside the mesocyclone, particularly at the lower levels, so more at 2 kilometers than at 6 and 10. Now, if we look at the worst misses, we're seeing the pattern here is much simpler. Tornado probability seems to increase with all radar variables inside the storm and decrease with all radar variables outside the storm. So it's saying if you want to increase tornado probability for these storms, you want to kick up all the radar values inside the storm and then get rid of convection outside the storm. So the GridRAD model seems to be picking up on the fact that, that more isolated storms are better tornado producers. Now, the final saliency map I'm going to show you is for the best hits, but now we're looking at the GridRAD model, we're looking at the MERS model instead of the GridRAD model. The format of the figure is the same, so solid contours mean positive saliency and dash ones mean negative saliency. So I'm going to start with the arrow at the bottom and work my way up, discussing the patterns I've seen. So once again, tornado probability increases with reflectivity inside the core, especially at the upper levels at 10 kilometers more than at 6 and 2. Tornado probability increases with rotation inside the mesocyclone. You see those really dark solid contours there, really high values of positive saliency with really high values of negative saliency just outside. So it's saying you want to increase rotation in the low-level mesocyclone, but then you want to get rid of rotation around that area. So you want to strengthen and contract the low-level mesocyclone, which is something that we know happens during tornadogenesis due to convergence and vortex stretching. So this could be picking up on that physical process. And finally, tornado probability decreases with reflectivity in the rear flank downdraft, especially at low levels. So that could be related to the negative buoyancy thing that I talked about earlier, where you don't want too much precipitation loading and evaporative cooling and negative buoyancy, making the RFD air too cold. The final interpretation method I'm going to talk about is backward optimization. All this method does, I'm not going to get into the weeds of it here, it creates a synthetic input that maximizes or minimizes the prediction coming out of your CNN, which in this case is tornado probability. So I'm only going to show you one set of results for backward optimization. I took the 100 best hits for the MERS model, and then I asked the CNN, I presented each one of these storms to it. So I presented the 100 storms individually, and what you're seeing here is a composite. I asked the CNN, hey, you've predicted a really high tornado probability for this storm. What would you do to decrease tornado probability for this storm? So on average, the changes the CNN made decreased tornado probability from 99% to 10%. You'll notice panels A and B are showing the original and synthetic radar image, so before and after backward optimization. And there's not a whole lot of difference. The main thing that was affected was reflectivity at 10 kilometers. It got rid of those values above 50 dBz, so it did make the reflectivity core weaker, especially at upper levels, and it filled in some reflectivity in this area at 2 kilometers where you would expect the rear flank downdraft, but not huge changes. But backward optimization had a lot of effect on the sounding, especially below 700 millibars. You'll see that it created a deep temperature inversion. It got rid of a lot of near surface moisture, so it decreased the relative humidity, and it decreased low-level wind speed and thus low-level wind shear. And all those things are important. We know to be important for tornado genesis from previous studies. One thing I'll note is if you look at the synthetic sounding, it doesn't look super realistic. It kind of has the jaggies. This problem was really bad when I applied backward optimization straight out of the box with no physical constraints. The entire sounding was just back and forth, high frequency noise. I applied a lot of physical constraints to alleviate this problem, but more work is done if we want to use machine learning to really create realistic synthetic weather data. So if we want to go to that next step. So that wraps up tornado prediction. So I'm going to get into part 2 here, which is front detection. I've used similar methods for front detection. Like I said at the beginning of this talk, I use convolutional neural nets, which are that deep learning method I use for tornado prediction. So a lot of the background stuff I gave you for tornado prediction, I'm going to skip past a little quicker here. So just an introduction to fronts for those of you who don't know or want to refresh your memory. Whenever I say front, I just mean synoptic scale fronts. They're important because they often trigger extreme weather, including heavy precipitation and severe thunderstorms. A front is a transition zone between 2 air masses with different thermal properties. And fronts are typically defined by some thermal field, temperature, wet bulb temperature, equivalent temperature, or the potential versions of those things. So front detection is typically done in one of 2 ways. It's done by hand analysis, where a meteorologist sits down with colored pencils and they draw on a map, or it's done by numerical frontal analysis, which is automated processing of grids using a bunch of derivatives. Both of these methods have some big disadvantages. Hand analysis is really time consuming. For the climatology I created, there's 117,000 time steps. Good luck convincing a human or even a small team of them to hand contour 117,000 maps. The big disadvantage of NFA, numerical frontal analysis, is it typically produces noisy results because it typically depends on derivatives and higher order derivatives, so second and third derivatives of a gridded field, and it usually captures only specific types of fronts. So for example, there's this paper back in 2015, they looked at a commonly used method called the thermal method, and they found it rarely detects warm fronts. It detects cold fronts much more often. So this has spurred recent efforts to use deep learning to do front detection. There's a list of papers there. What makes CNNs well suited for front detection, like I said earlier, is they can directly process spatial grids. So they can look at gridded data and paint in the warm and the cold fronts, which is what I've done. So I'm going to talk about the input data for a couple slides, and then I'll talk about some details of the machine learning and show you some results. So I've used 2 data sets with 3-hour time steps. The ERA5 reanalysis I've used to create my predictors, and the WPC, or Weather Prediction Center, surface fronts, which come from the WPC surface bulletins I've used to create labels. Those are drawn by human meteorologists every 3 hours. I use 4 different ERA5 variables as predictors at the surface and 850 millibars, so I have 2 levels there. The variables are temperature, specific humidity, and then the wind vector, U and V. So in this figure at the right, I'm showing you the predictors at the surface level. The warm and cold fronts here are those drawn by humans at the WPC. And then instead of showing you temperature and humidity in 2 separate sets of contours and making this map super busy, I'm just showing you theta W, the wet bulb potential temperature, which combines information from both. And then if we go to the next slide, the only thing that's changed is now you're seeing the predictors at 850 millibars. So this is the data that got fed into the CNN to allow it to do its thing. So each input to the CNN was a small patch. It wasn't this entire grid. It was a 33 by 33 grid cell patch, which is 1,056 by 1,056 kilometers. You can see one of those patches here on the right-hand side. And then the label, or the correct answer to be emulated by machine learning, is what type of front, if any, passes through the grid cell at the center. Could be a warm front, it could be a cold front, or it could be neither. And then I used grid search, like I did for tornado prediction, to optimize some hyperparameters at the CNN. I did that here to optimize the predictors. So I tried U and V wind, temperature, specific humidity. I also tried training with geopotential height, Z, and wet bulb potential temperature, which is that theta W. I tried different vertical levels. So I tried training the CNN with surface data and pressure level data from 1,000 up to 850 millibars. And I tweaked the number of convolutional layers anywhere from 2 to 12. And for front detection, I ended up not using data augmentation because I found that it unanimously made things worse every time I tried it. I think the reason is I had much more training data for front detection than tornadoes because fronts are a less rare event. And on this slide, you're seeing the predictors at 850 millibars instead of the surface. Going to take a swig of water. So here, you're seeing the CNN architecture that I use for front detection. This flowchart is similar to what I showed you for tornado prediction, just different layers and a different task. So I have my input, which is this 33 by 33 patch with predictors at the surface and 850 millibars. And it goes through convolution, convolution pooling, convolution, convolution pooling. And then all those spatial features that are found by the convolution and pooling layers are flattened into a 1D vector. That's fed through 3 dense layers at the end. And that transforms this set of features to 3 probabilities, which are warm front, cold front, and no front probabilities. And those are constrained. I use something called a softmax activation function to make sure those probabilities all sum up to 1. So to apply the trained CNN to a full grid, I slide that 33 by 33 patch window around and just center it on every grid cell to create this probability field that you see down here. Red colors are warm front probability, blue colors are cold front probability. And then before creating the climatology, which I'm going to show you next, I apply a probability threshold of 65% to create frontal zones. And then I apply a length threshold of 200 kilometers to get rid of anything below synoptic scale. So you'll note, as you go from the center panel to the right panel, that got rid of this tiny little cold frontal zone, off the coast of California. And here's a little GIF. This is an animation over 6 or 7 days of the fronts that are detected by the humans and the fronts that are detected by the CNN. One thing you'll note is the fronts detected by the CNN have much more temporal continuity. If you look at the human drawn fronts, they often just disappear at one time step and reappear at the next time step. Whereas the CNN has managed to overcome that deficiency in the human drawn fronts. So now I'm going to talk about the climatology. That's the last thing I'm going to show you today. And this is going to be kind of a 3-part end to my talk. So I'm going to show you, I've created 3 different analyses for warm front and cold front frequency. I'm going to show you averages over the 40 years, which are 1979 to 2018. So the 40 years in the post-satellite era. Variability relative to the El Nino Southern Oscillation or ENSO phase, and also trends over the 40 years. When I say frequency, I just mean the percentage of time steps with a warm front or a cold front passing through the particular grid cell. So here I'm showing you the average cold front frequency for each season. So there's winter, spring, summer, fall, as you go from panels A to D. There's a few things I want to note here, a bunch of regional patterns that I don't have time to talk about, so I'm going to focus on the large scale. Cold fronts are most common in the mid-latitude cyclone tract, that big swath extending over the Pacific and the Atlantic Oceans. That mid-latitude cyclone tract shifts poleward by about 10 degrees from winter to summer. You can see that by comparing panels A and C, and it does that due to the global annual heating cycle. So during summer, baroclinicity shifts towards the poles and then back towards the equator in the winter. And you also see this weird maximum in summer cold fronts in the eastern tropical Pacific. Cold fronts never reach this far south except in that area. And so I've looked at these cases individually, and I found that these fronts are due almost entirely to moisture gradients instead of temperature gradients. They're due to invasion of dry subtropical air, so air that subsided under the tropical high and starts invading into the tropics. There's a previous climatology from Barry et al. In 2011. They found a similar pattern, and they made the same conclusion, that these fronts were dominated by moisture gradients. So going to the next slide.
Infrared radiation, and it spectral and temporal.
I'm sorry, I didn't catch that. Okay, I'm going to move on because that cut in and out for me. I don't know if there was a question or not. So on this slide, I'm showing you average cold front frequency by season. The next slide, I'm showing average warm front frequency by season. You'll note, like cold fronts, warm fronts are most common in the mid-latitude cyclone tract, and the large-scale maxima and warm fronts that occur in that cyclone tract are shifted about 10 degrees north of the cold front maxima. So if you go from this slide to the next one, you can see that big northward shift. And that's consistent with mean frontal positions relative to their parent cyclones. Warm fronts tend to be further north than the cold fronts. Also, warm fronts at land-sea boundaries occur much more often than cold fronts. For example, if you look at the winter panel A here, there's this maximum along the Gulf Coast. I did look at these cases to make sure that stationary fronts that are just there all the time because of the land-water temperature gradient aren't being misidentified as warm fronts. and they're not. These things are identified as warm fronts by the CNN only when there's warm advection across the boundary, but it doesn't happen as often when there's cold advection across the boundary. I think the reason is the CNN has learned from all these cyclonic examples in the mid-latitude cyclone track that cold fronts tend to be stronger. They tend to have stronger thermal gradients and stronger advection. So it takes more advection across a land-sea boundary to get to that cold front threshold than it does for a warm front threshold. So the second part of the climatology here is variability relative to INSO.
Ryan, can you hear me? It's Jason.
Barely, yes,
Oh,
I can hear you. I'll cut my ear.
Sorry. Hello.
Yes.
Speaking in right into the thing. Can you go back to the last map?
Yep.
Please? So am I interpreting this right, that the western part of North America receives no fronts?
Yeah, if you're, oh yeah, if you're looking at the Mountain West.
Well,
yeah,
even like British Columbia. Am I interpreting? I can't tell the colors if that's white from the 0, or is that white on the 1? I can't really tell there.
Okay, my apologies. Yeah, that's white from the 0. So
From
yeah,
the
what
0
this is suggesting.
in British Columbia and on the coast there.
Yeah.
Okay. So are you saying that places like Vancouver and Victoria receive 0 warm fronts ever?
That's the CNN is saying that. So that's probably a deficiency of this method, is that I've used the same definition and the same threshold to detect warm and cold fronts everywhere. So it's the model is spatially agnostic because it's trained on a 33 by 33 patch without knowing where it's coming from. So I think if I had done, if I had created a non-spatially agnostic version of this model where it knew about the underlying geography, that it may be able to get those fronts a little better in the Mountain West. I did at one point try training with orographic height as one of the input fields, and that improved things a little bit. It led to a few more fronts being detected over the Mountain West, but there was still this big minimum there.
Okay. And my second just quick question, I'm sorry for interrupting. I didn't quite get from the talk and also from the dissertation how you handled occlusions in the human forecast versus how, like, what you did with them in terms of comparison with your front analysis from the CNN.
Okay, occlusions were considered, they fell into that other category, which is NF. So this was 3-class classification. So
okay.
What the CNN was predicting was warm front, cold front, or neither. So occlusions fell into that neither category, and also stationary fronts that were labeled by the humans fell into that neither category.
Okay, thanks.
Thanks.
Hey, Ryan.
Yeah.
You had a comment in the chat about Jason's question. I guess it was related to the same question. You can go back one slide.
Okay.
Asking about if you had any data issues at the 850 hectopascals in the mountain.
Yeah, that's probably where part of this is coming from. I mean, I use surface data as well. And obviously surface data is available everywhere because you're not extrapolating underground. But using the 850 millibar data did probably cause an issue here.
That's it. That's the only comment there. So.
Okay. So part 2 of the climatology is ENSO relative variability. So how front activity changes during El Nino and La Nina. To refresh your memories, or in case you don't know, ENSO is an irregular periodic variation in sea surface temperature, or SST, across the equatorial Pacific. The 2 phases are El Nino, where the eastern Pacific is warmer than usual, and La Nina, where the eastern Pacific is cooler than usual. Excuse me. So here are the effects that we would expect El Nino and La Nina to have on fronts just a priori. So El Nino leads to more convection in the eastern Pacific because the sea surface is warmer. That leads to a strengthening and contraction of the Hadley cell due to that tropical heat source. That leads to a southward shift of the subtropical jet as the edge of the Hadley cell retreats towards the equator. And that causes the mid-latitude cyclone track, which is associated with the jets, to shift southward as well. So those red arrows in the top panel are showing you sort of the anomalous jet that happens during El Nino. And during the winter, when the subtropical jet is at its southernmost extent, this also causes an eastward extension over the Gulf of Mexico. The effects of La Nina are roughly opposite to the effects of El Nino. So we would expect a northward shift instead of a southward shift. So I've defined ENSO phase using the standardized anomaly of the Niño 3.4 index using detrended sea surface temperatures from the Climate Prediction Center. So I've defined the neutral phase as when Z is between -0.5 and +0.5, then strong El Nino as Z being at least 1, and strong La Nina as Z being less than or equal to -1. So I'm going to show you some composite differences in both warm front and cold front frequency. I'll show you strong El Nino minus the neutral phase, and then strong La Nina minus the neutral phase. I've done a Monte Carlo test to find significant grid points, and I've shuffled entire spatial maps together instead of doing it separately at each grid cell, which controls the false discovery rate that would come from multiple comparisons. I'm focusing only on the winter and spring when ENSO teleconnections are the strongest and I have the most statistical significance. So here you're seeing the effect of strong El Nino in winter. Red means increasing front frequency, blue means decreasing. So you see this in both maps for warm and cold fronts. You see this red swath to the south and blue swath to the north. So increasing to the south, decreasing to the north. That suggests a southward shift in front activity, which is consistent with the southward shift in the subtropical jet and the cyclone track. Also, the increased front frequency over the Gulf of Mexico is consistent with an eastward extension of the subtropical jet. There was another paper back in 2003 that investigated just cold fronts in the southern United States and Gulf of Mexico. They found a similar pattern, but without statistical significance. Also, you see increased warm front and cold front frequency over Hudson Bay and some of the Canadian subarctic here. That may be due to an anomalous polar jet stream in that location that forms during El Nino. And now you're seeing strong La Nina in winter. So going from El Nino to La Nina, instead of seeing blue over red, you're now seeing red over blue, not with as much coherence in the pattern, especially for warm fronts, but this does at least mildly suggest a northward shift in front activity during La Nina, which would be consistent with the northward shift in the subtropical jet and cyclone track. Also, over the Bering Sea, you can see increased warm front frequency with a decrease along the south coast of Alaska in this green circle here. That could be due to La Nina shifting the position of the Aleutian low westward, so that warm advection around the eastern flank happens in the Bering Sea and not over the Aleutians. That shift of the Aleutian low was found in this paper from Niebauer in 1998. The La Nina results are weaker and less significant than El Nino. There's much less stippling here, probably because La Nina is less common, so the sample size is smaller, and La Nina has weaker teleconnections associated with it. And the results for winter El Nino and La Nina, the last two slides that I've shown you, are broadly consistent with the previous climatology from Rudeva and Simmons back in 2015. To my knowledge, that's the only study that's investigated the influence of ENSO on front frequency on such a large scale. And now I'm showing you strong El Nino in spring. So if you go back 2 slides, this is winter. Jump ahead 2 slides, this is spring. The pattern is similar, suggesting a southward shift again. The main exceptions are that the spring response is weaker and significant grid points cover a smaller range of latitudes. That's probably because spring has weaker SST anomalies than winter. Those SST anomalies that define ENSO typically peak in winter and then wane throughout the year. And also in the spring, as opposed to the winter, you have weaker westerly wind that connect the mid-latitudes to that tropical heat source to carry the teleconnections and the Rossby waves from that tropical heat source to North America. So finally, the third part of the climatology, I'm going to talk about long-term trends. One would expect that this is what I was expecting / hoping to find, the effects of global warming on front activity. One would be a poleward expansion of the Hadley cell, which has been suggested in a lot of recent papers. That would cause a poleward shift of the subtropical jet associated with the Hadley cell in the mid-latitude cyclone track, and that might cause a poleward shift in front activity. Also, Arctic amplification is a well-known feature of global warming. So that would lead to a weaker temperature gradient at higher latitudes as the Arctic warms more than the surrounding areas, and that would lead to less baroclinicity and possibly fewer fronts at higher latitudes. So for each season, I've computed the linear trend in warm and cold front frequency using a Mon-Kendall test, and I found the significant grid points. I used a method to control the false discovery rate. Unfortunately, the method I used was overly conservative, like most methods for controlling the false discovery rate, and it led to a really low p-value threshold. So most of my results weren't statistically significant. So due to that, I'm going to show you winter only. And even then, most of my results aren't statistically significant. So only spending 1 slide on them here. The pattern you see is suggestive of a northward shift in front activity over the last 40 years, which would be consistent with that poleward expansion of the Hadley cell, the northward shift in the subtropical jet and cyclone track. And also you do see decreasing front frequency over the Arctic, but it's a really weak signal and statistically significant almost nowhere. There are 2 previous climatologies that have investigated the long-term trends of front activity. they found similar patterns, but with a lot more statistical significance. There is one big discrepancy. There's this study from Berry et al. In 2011, and instead of finding a northward shift over the Atlantic Ocean with this alternating blue-red pattern, they found a general decrease in front activity over the Atlantic. So that's something worth investigating in the future. Also, by applying a CNN to climate model output, like a full 21st century projection, containing a longer time period, you could maybe find more significant and different results. So I'm just going to wrap up with 2 slides here, summarizing and alluding to some future work. So I've developed and tested CNNs, which are a deep learning method for tornado prediction and front detection. The tornado models I found perform competitively with another model, a machine learning model that's currently used in operations. The failure modes for my CNN are non-tornadic supercells that make up the false alarms, and then tornadic QLCS cells, or quasi-linear convective system cells, that make up the worst misses. Both of these failure modes are difficult for humans as well. I use several interpretation methods to look at what the CNNs learned. Those highlighted physical relationships that have shown up in previous numerical modeling and observational studies, things like the depth of the reflectivity core, the strength and compactness of the low-level mesocyclone, the discreteness of the storm, and reflectivity in the rear flank downdraft. Some future work is operationalizing these models so they can be used by humans in real time in the hazardous weather testbed. Comparing human interpretations versus CNN interpretations is something I really want to do as a trust study to one, make sure that the CNN interpretations are highlighting legitimate physical relationships, and 2, to see if maybe we can use interpretation methods to guide the discovery of new knowledge. We'll never be able to completely automate the knowledge discovery process with machine learning, but to flag new hypotheses maybe. There's this paper from Wagstaff and Lee in 2018 where they used it to flag novel exploration targets for the Mars rover. So something like that I would like to do, and also improve the performance of the models for QLCS tornadoes. There's a few papers where this work is presented, listed at the bottom. Finally, for front detection, I've trained a CNN to draw warm and cold fronts and reanalysis data. I created and analyzed a 40-year climatology over North America. I just discussed all those results, so I'm not gonna restate them. Some future work is operationalizing the front detection model as well for real-time use by forecasters. There's a proposal underway where hopefully we get to do that. Also, I'd like to investigate front activity in a future climate. So instead of looking at reanalysis data, identify fronts and climate projections, and also investigate the climatology of front-related extreme weather and figure out where, where certain things like heavy precipitation and severe thunderstorms are related to fronts. And there's 2 papers listed at the bottom where some of this work is presented. Finally, I'd like to acknowledge my committee chair, Amy McGovern, who's been an excellent, wonderful, incredibly supportive advisor. I've been very lucky to have her for the last 6 years, and some other people who provided input and data throughout this project: David John Gagne II, John Allen at Central Michigan University, Cameron Holmeyer, Brian Williams was the host for my Google internship. My friends and family, the WEX Twitter and academic Twitter communities have been incredibly supportive, and all of you for showing up today. Also my cats, Hypatia, Eratosthenes, and Hedwana. They're all named after scientists. And yeah, that's it.
So virtual clapping, since we're not going to all unmute and clap. What I think we'll do is we'll open up. Oh, we can applause. Oh, there's an applause button. Okay. What I wanted to do was open up to the general audience. Some participants have dropped off, but you, by the way, reached a maximum of 101. You have one in the questions. Ellie, do you want to ask your question first?
Yeah, I can just ask this real quick. I have to go to another meeting, but in your front trends, how many actual fronts have either increased or decreased, like over the past 40 years? I noticed you had a trend per 40 years and numbers of like 0.01, and I just couldn't figure that out quickly in my head, right? So if it's a increase of 0.01 and it's significant, is that how many actual fronts more would you expect to see?
So that's
that makes sense.
Yeah. So some confusion has come from this in the paper as well about whether it's a relative increase or an absolute increase. This is an absolute increase. So for example, if the trend is 0.01, that means if the front frequency at a given point is 7% now, you would expect it to increase to 8% over the next 40 years. So if that grid cell is getting front 7% of the time now, it would get a front 8% of the time in the future. So in terms of number of fronts, since this is fraction of 3-hour time steps with a front passing through the grid cell, a change of 1%, there's 2,920 time steps per year if you slice it up into 3 hours. So 1% would be about 29 more fronts per year. But that would be 29 more time steps per year with a front, but those would not necessarily be 29 unique fronts, if that makes sense.
Okay, yeah, that makes sense. That's why I couldn't do that in my head quickly. Thank you.
Any others from the general audience? I think you had a request in the chat window to go back and look at tornado outputs.
Okay.
Matthew, if you're still there, do you want to ask a question about them, or did you just want to look at them?
Which outputs? The rock curves, performance diagrams?
I don't know. Matthew, are you still there? I'm not sure he wants to unmute. He just says wants to look. First thing you said.
Okay.
Is this the right thing, Matthew? Yes, he says. Okay.
Okay.
And are there other questions? I guess he just wants to look at this. He didn't seem to have a question. Are there other questions from the main audience?
Amy, I have a question. Dave Parsons here. First, a comment. I wanted to thank Ryan for being a resource for other people interested in deep learning in the community. So that's wonderful. My question is to do with the climate change. The weakening baroclinic strength of the baroclinicity across the Arctic front, let's say, or Arctic to polar or to mid-latitudes. I would expect weaker fronts, but it's not clear as to what's the mechanism for less fronts. I think some models actually have a change in the nature of the cyclones and their location rather than. So what's going on to make less fronts, and have you looked at frontal strength? Is there a way to do that?
I think my answer to your question is a two-parter. So for one thing, I mean, there's lots of different ways of defining fronts, and generally there's some sort of minimum strength threshold, whether it be on the temperature gradient or temperature advection, wind shift, whatever it may be. So that's kind of baked into the CNN as well. So usually if you see a if you see a really weak temperature gradient, it's not going to be detected as a front. So the temperature gradient or advection, whatever, frontal characteristics in general, they have to be strong enough for that feature to be detected as a front. So there's a good chance that there are still weak fronts occurring in that area that just aren't being picked up by the CNN anymore because they've gotten weaker. The answer to part 2 of your question, whether or not I'm looking at front strength directly, I've kind of done that. So what I found is that the first thing the CNN outputs before I turn everything into deterministic frontal zones is it outputs these 2 probability fields. And I found that generally the probability it outputs is proportional to the strength of the cold front or the strength of the warm front. Of course, that strength is being defined subjectively by me as a meteorologist looking at a map. So I found that when my default probability threshold, which I tried a whole bunch of different ones, my default here is 65% before I'm willing to call the thing a warm front or a cold front. I found that when I decrease the probability threshold to 50% or increase the probability threshold to 80%, the results I get for the climatology are quite similar, except that the changes are mostly confined to the mid-latitude cyclone tracks where fronts tend to be strongest.
Thanks.
You have 2 in the chat window, one from Aaron Kennedy, who asks if all 12 levels are needed for the tornado work, or could you save computational time by selecting a few key levels, and what to do when radar data is missing?
That's a good question. So for part 1 of that question, I've tried to save computing time in the past by doing that, by not using all 12 heights. So what I was doing a while ago is I was taking layer operations. So I defined the low level as 1 to 3 kilometers, and the mid level was 3 to 6, and the upper levels were 6 to 12 or something like that. And I took maxima and minima and things like that over the layers to turn this 3D data into 2D data before I fed it into the CNN. And what I found was that my performance got worse. So where I was showing you the results for tornado prediction earlier, I showed you this rock curve and performance diagram. and I have an AUC of 0.94 for both of the models. When I did that whole layer operations thing to decrease the data from 3D to 2D, my AUC went down to like 0.88, which was as you can tell by the width of these confidence intervals here. Sorry, I didn't mention this earlier. There's 95% confidence intervals on these curves. So a change from 0.94 to 0.88 was a pretty significant decrease. So I felt that decrease in computational complexity wasn't worth it because of the decrease in performance. And then, sorry, what was part 2 of the question? Oh,
handle missing data.
What to do when there's missing radar data. Honestly, I'm not sure about that. I think to some extent I've controlled for missing radar data by doing storm tracking. So when I was showing you the pre-processing stuff earlier where I've outlined storms and I've tracked them over time, the tracking, the field that I used to track these storms was 40 dBz ecotop, and that had to be at least 4 kilometers above sea level. And that had to be over an area of at least 5 grid cells for the thing to be called a storm. So chances are if there's missing radar data, the storm is just not going to be tracked, so it's going to be dropped.
Okay, you have 2 more questions in the chat window. One is, I'll go in order, although the one after it is more related to what you just said, but Brianna is asking about the Gaussian noise, so your data augmentation.
Okay.
And why you did it.
Okay, so the whole point of data augmentation is that it's another method to control overfitting. So if you don't do data augmentation, the idea is the CNN could learn very particular relationships, especially when you have a small data set, which in this case, in terms of the total number of storms, I don't have a small data set, but in terms of the total number of tornadoes, because tornadoes are a rare event, I have a much smaller data set. So generally when you have a small data set, you're not sampling the full range of possibilities. So to kind of get around that, you're not increasing the effective sample size as much as you're increasing the nominal sample size. But a way to kind of get around that is use data augmentation and pretend that if you apply little tweaks to these storms, the outcome remains the same. So it doesn't change their potential to produce a tornado. So that's the purpose of doing these rotations and translations and adding Gaussian noise, is I'm saying, I want the net to learn, even when I've applied this small amount of Gaussian noise, the label stays the same. So a tornadic storm is still tornadic, a non-tornadic storm is still non-tornadic.
I was just responding to one of them in the text. Matthew's next question, which I gave him the response about our pending jetty, but you can answer the other half, which is how to integrate this into a real world scenario, sort of how you get the data going. He says, are you going to use a composite of all the radar sites? Parentheses, yeah. Kind of.
Okay, yeah. The answer to that is that, so as I mentioned throughout part 1 of the talk, there's these 2 radar data sets that I trained with. One's called GridRAD and one's called MIRS. There's a real-time version of MIRS that's called MRMS. Excuse me. It means multi-radar, multi-sensor. And they do this radar compositing in real time. So they take data from all the WSR 88D radars in the country, which are back here. And they do this composite every 2 or 2.5 minutes. So there's a real-time version of MIRS. What remains to be seen is if I can just take the model that's trained on MIRS data and apply it to MRMS data, and if it will do well enough. If not, there's a chance that when we take this model and want to apply it in real time, we'll have to retrain the model on MRMS data instead of using a model trained on MIRS data. But yes, this could definitely be applied in real time. The other data set I used as input was the proxy soundings from the RAP weather model. That's available in real time. I made sure I was always using data from before the forecast time, so data that would be available if you were doing this in a real-time setting. So yeah, all these data sets are available in real time, except if you just replace MIRS with MRMS. Right,
and we have a jetty pending that will work on some of that as well. So, but you know, hopefully we get reviews and get funded this month with the world.
For the people who are unfamiliar with that, jetty is a joint technology transfer initiative proposal. So, to take research products and put them into operations.
Any more questions from the audience? Okay, If not, I think what I'll do is I'll stop the recording and then we'll just go down to the committee. But for the committee, I think we'll give you all a bio break because, you know, we've been sitting here. But so give everybody a 5-minute break and come back. Does that sound good?
Okay.
I'm going to stop the recording.